Okay. So thank y'all for sticking around. Maybe it's apt that I am the last presenter because I'll be talking to you about air travel, and I think there's a decent number of you who are flying out either later today or tomorrow. So maybe AI aside, I'll try to impart some air transportation knowledge. So what I wanted to talk to you today about is, when I was submitting for this presentation, I was kind of given the feedback that maybe focus a little bit more on sort of how you engage with the stakeholders, of your research to kind of bring AI into the fold here. And specifically, in this case, the stakeholders would be the Federal Aviation Administration. So it would be the folks in charge of making sure that your plane gets from A to B safely and efficiently throughout your journey. So what we've been doing is we've been working with the students have been really leading this project on trying to see if there are good uses of large language models within the realm of air traffic management. So what I'll try to do today in this presentation is get you some working knowledge of what exactly do I mean by air traffic management, and then talk a little bit about the engagement process that we had with air transportation stakeholders as we went along. So I think in terms of the at least the one picture in my head of air traffic management, which I think about all the time, is this picture here. So it essentially boils down to trying to maintain balance between demand, so people who want to fly, maybe some of you in the room today, and then the supply that is able to accommodate your flight. So in this case, it could be runway capacity. So how many airplanes can that airport support in terms of takeoffs and landings? It could be the number of gates that are available at your airport, and so on. So maintaining this balance is really the crux of air traffic management, and the various techniques that are employed for air traffic management. And this is becoming more and more sort of applicable. This is, of course, these are sort of pre-COVID data, but if you skip the trends after COVID, it's continuing along the same lines. So essentially, you can get to more places for less money. Okay, this is, of course, inflation adjusted and so on. And I was talking about this with some of the folks here. As people move into the middle class, a lot of surveys have shown one of the first things that they want to do with their newfound disposable income is to take advantage of the air transportation system to air travel. Okay, so this is kind of good news for me. I love planes and I love seeing them being used, but of course there's a cost in terms of both congestion. So we build our systems assuming a certain capacity. Of course, when they're exceeded, you get congestion, and when there are congestion, there are real and indirect costs, both to the passengers as well as to the airlines. And then, of course, there are also the potential for environmental costs as well. One of the classic examples, and I'll actually show you an example with Dallas Fort Worth International Airport. Maybe some of y'all have had situations where you've come off the gate pretty on time, and you ended up sitting in the airplane, sitting right by the runway, waiting with your engines on, which of course is consuming fuel and producing environmental emissions. So this is the system that we have today, and this is really the system that we are trying to see if we can bring in some interesting solutions from AI, from large language models and so on to help improve. And to give you a sense of what the awesome folks in our air traffic control towers, our air traffic control facilities are dealing with every day, let me just take you to that example that I have for Dallas Fort Worth. So some of you might have flown through this airport before. It's a huge hub for American Airlines. It is their biggest hub. And it is quite an impressive piece of infrastructure just on face value. Even though there looks to be quite a lot of runway capacity, quite a lot of gate capacity as well. Let me show you what happens when there is the occurrence of bad weather, of severe thunderstorms around the Dallas metro area, which is quite common in, especially in the spring and summertime. So what you're going to see play next is from one of the FAA radar systems. It's a little poor quality, but essentially the blue tracks are departures out of Dallas-Fort Worth, and the red tracks are arrivals into Dallas-Fort Worth. And as you see that patch of pretty bad thunderstorms, which planes don't like to fly through, as it goes over the main area of Dallas, we start seeing quite a bit of holding patterns that the planes are starting to execute. And you'll even start seeing some of the red planes fly away or fly to other airports because they're not able to actually land at Dallas-Fort Worth, and they're getting into a spot where they're starting to run low on fuel. And this is all kind of coordinated manually, right? So now from the strategic traffic flow management perspective, where we're balancing demand and capacity, where we try our best, but maybe we don't succeed because we didn't predict that this thunderstorm would be quite as bad, then the planes get here, there's no capacity for them to land, and now you get to the level of tactical air traffic control, where controllers are telling planes, we're basically manually starting to vector these planes appropriately. Something that you'll see happen sort of in the middle of the screen is you'll start seeing planes fly these S-shaped patterns. You'll see these spirals start to appear on the screen. So that's literally the air traffic controllers trying to slow the planes down and trying to wait out the storm passing through. So incredibly manual process, everything from the kind of the strategic demand balancing part all the way to tactical flow management. At the surface, it doesn't become any easier. So this is on another different day at Dallas. And basically what happened on this day is the winds shifted very rapidly, which resulted in Dallas having to use a different set of runways. And something like a queue of 30 to 40 aircraft started building up, waiting to depart the departure runway. So now you start seeing those on the right-hand side trying to depart on on the runway on the right, and then a massive queue on the left-hand side as well. So again, all of these aircraft are waiting on the taxiway with engines on, right? Again, if we could kind of do traffic flow management a little bit better and more effectively, we can potentially try to avoid some of these situations. And then I'll throw in a bonus example from JFK. This was just a few days ago. This was back, I think it was Monday or Tuesday, something relatively recently. There was low visibility wind conditions at JFK, and there was basically a double queue of about 20 to 30 aircraft each. Again, wasting fuel, kind of spending it on the taxiway here. So the reason why, this is kind of a gnarly problem to introduce AI to is, and I'll introduce some of the reasons for why it's taken kind of a lot of interactions, one step forward, two steps back with stakeholders. One, there's just a lot of stakeholders involved. So when we think about what it takes to coordinate kind of a large network system like this, there's of course the air traffic control portion. So this is in the US, it's the FAA. Of course, each country, each region has their own set of air traffic control facilities and air traffic control authorities. A lot of the times, the technology that is currently being used can be a little antiquated, and it may not be. There might not just be the data input that you need for a fancy AI algorithm. Okay, so just getting a sense, going to the command center in Washington, D.C. or an hour outside of Washington, D.C. and seeing, some equipment looks super new, some equipment is like 1980s stuff. So just seeing kind of the discrepancy and trying to work through that can be challenging for a researcher like myself trying to think about how to optimize the system and do better. And then it turns out there are about 7 or 8 children running around in the system that are actually utilizing the system. In this case, it would be the airlines. All of these airlines also have their own disparate set of systems, some newer, some older, some more centralized, some less centralized, some more amenable to use in AI settings, some less amenable to it. So kind of this brings a whole additional layer of complexity. These are the users, and not only are they users, they also are competitive users, right? If I think about Chicago O'Hare as an example, that is essentially a capacity competition between United Airlines and American Airlines. Okay. To make matters even more complicated, they are not the only users of the airspace. So the Department of Defense, as an example, is a big user of some of our airspace. A common issue that's been occurring lately in the U.S. airspace is right around Florida. So essentially, the Florida Panhandle region, to the left and to the right over those bodies of water, those are restricted military airspace that are often closed for military exercise, which ends up funneling all the traffic over the Panhandle. You throw in a couple of space launches out of Cape Canaveral. You throw in some thunderstorms that come right up the Panhandle, and it becomes a major bottleneck within the system. So, and then finally, we have to play nice with our neighbors as well. So we have both Mexican air traffic control and Canadian air traffic control to the north and the south. So there are coordination that's needed with these entities as well. And again, every single every single stakeholder here. Systems are of varying levels of antiquated or not, able to handle kind of the latest and greatest AI. So it's a mismatch. So this is kind of what makes it hard, and it results in me and my students having a lot of conversations with a lot of stakeholders trying to understand what do you have, what do you not have, what are you able to do, what are you not able to do, and so on. Yes, so I'll spend the last kind of 5-10 minutes of my talk just giving kind of a brief overview of where we have found a nice niche problem because essentially the moment you talk about AI in an air traffic control setting, people have one of two reactions. They either say, oh, this is super cool, we definitely need this, or they say, I'm calling the union, do not replace my air traffic controllers, right? So it's one of the two reactions, and it's always an interesting balance of which one we get. So we definitely didn't want to touch things like replacement of human air traffic controllers or traffic flow managers. What we wanted to do was how can we leverage large language models and AI to help you with your everyday life, okay? So that was sort of the angle that we kind of went into this with. So I'll skip through some of this because we've talked a little bit about air traffic management already. Essentially, you want to get from A to B, but there might be a capacity constraint or supply side constraint. And how do you manage the demand effectively? One way that we manage demand here in the U.S. is and also in other places in the world is relatively simple. If you're trying to fly from Detroit to New York, and you know New York is going to have an issue with how many planes it can land, you want to stay in Detroit with your engines off as much as you can until the point where you can depart Detroit and get to New York without doing airborne holding, because you would rather wait on the ground than wait in the air for fuel savings, for safety reasons, for airspace complexity reductions, and so on. So the name of the game for a lot of this traffic flow management is, can I predict my capacity constraint well enough to shift delays into a less costly place in my system? That's kind of the whole name of the game. And very confusingly, we call these GDPs, ground delay programs, and it's essentially a way, again, to slow the rate of arrivals into a particular airport. And there are a couple of main parameters which make GDPs very appealing from a kind of a data science mathematical perspective, which is all of these delay programs have a start and end time. They also have a arrival rate. So during the period of this program, I can land 25 aircraft per hour or whatever it is. So very numerical, very easily put into a database and very easy to analyze. What's not easy is that there's also oftentimes human written commentary about this delay program. So for example, you could write, hey, there's also runway construction today at Newark Liberty International Airport, so this program will be a little bit weirder than normal. And that's kind of in plain text. That's not really, in a nice, a categorical data or anything. It's just a sentence or maybe even 3 or 4 sentences written by a human being. Okay. I'll skip this, but this is essentially, this is actually a screen grab from the program. Talk about looking a little antiquated. It's literally the program that the FAA uses to manage demand, where the bars are the demand, the line is the capacity, the bars exceed the line, so how do we flatten the bars? Okay, how do we flatten the demand out? Okay. So what we've identified, again, talking with the stakeholders and trying to understand, how can we help them with respect to using large language models, we've basically boiled this down and boiled their work process down to 2 parts. So when they are evaluating demand supply imbalances within the airspace, they sort of think about this from the perspective of what's repetitive and what's unique about this circumstance. And repetitive challenges could be like bad weather around New York in the summer. That's pretty common. Okay. A unique circumstance might be, well, today there's a Super Bowl going on, so there's demand patterns that we're not used to seeing. There's a presidential movement, so maybe the president's flying somewhere and then there's a temporary flight restriction where the president is. Maybe there's a space launch, so there's additional restrictions around the Florida coast or wherever they're launching. So our thought was, can we take, the past history of ground delay programs, train a GPT with it, and then basically have it act as a little chatbot for you to try to get rid of this repetitive part so that you can spend your time and you can spend your brain power on designing a delay program for today's unique circumstance. So trying to kind of automate away the boring 50% of their work process and helping them focus on the more exciting parts. So that's essentially how we looked at this. So before, essentially, a traffic flow manager would try to recall from memory, like, okay, last time there was a wind situation at Newark, what did I do? And then this is the part that really forms the foundation of what they are going to plan for today. And then they basically layer on top of that, collaborative discussions with other air traffic and airspace stakeholders before implementing the delay program. What we want to do is we want to say, can we put this part, and instead of having the traffic flow manager kind of recall from memory, can we instead help them with essentially a LLM that they can interact with? Again, the philosophy here is, I don't expect the traffic flow manager to type in a SQL query to query every single similar day from the past 20 years and get a result. I want them to be able to type in a natural language question and get a nice human readable result that can tell them, again, trained based on the past 20 plus years worth of what we have done before. Okay. And what I want to emphasize here is, I'm not arguing that historically our actions are optimal, because they're probably not. Okay, so the historical actions need not to be optimal, and it's not that I'm asking the LLM to implement this program. I'm only asking the LLM to provide some lubrication for the thought process of the human traffic flow manager so that they can maybe spend some more time thinking about tailoring this program for today's mess, essentially. So basically the rest of the process here is the exact same. It's just that kind of initial part that I would like to see if we can introduce some help to. So I know I'm running a little short on time, so I'm just going to flash up just a couple of screens here. Again, we ended up doing a lot of user interviews because we wanted to understand, if I gave you this tool in your hand, you have this chatbot on your phone and while you're at the command center, how do you actually use it? How would you interact with it? What kind of questions might you ask? Then some of the rest of this, I think, is relatively straightforward in some sense, which is, okay, we needed to collect 20 years worth of data. We needed to fine tune the LLM that we wanted to use, and then we needed to do some A/B testing to see like did our fine tuned model, like did the output of this model give you something useful compared to a standard chatbot. So again, I'm gonna go forward a little bit to just try to finish up. So I will flash up this slide, which is kind of what exactly did we collect. So we ended up collecting about, as I said, 20 years worth, specifically from basically January 2003 until December of 2023. So about 20 years worth of historical ground delay program occurrences. This ended up being about 80,000 text files that we needed to clean and process. And each text file looked like this. Again, a lot of this is kind of nicely, you can put it into a database, which makes it open for things like retrieval augmented generation, etc. But then there were these comments. This is a particularly long one. There was a lot of comment here. Which I think the LLM, I'm not quite sure what it's doing, but it's at least giving a nice human interpretable output that the traffic managers will look into. With that, I think that is, let me just flash to the last slide here. Essentially what we're working on now is we've gotten some feedback that instead of just seeing like text output from the LLM, they wanted to see kind of a graphical output as well. So we're working with, how do we put this into the correct API and get the right user interface out. With that, I promise I am done. Let me move forward here. Yeah, so next steps, as I said, app development, and then looking into trying to make sure that it doesn't hallucinate too much and trying to conform it to just retrieving from a SQL database of previous parameters. And with that, okay, I am actually done. So thank you, and happy to take questions offline or now.
Okay, who has a question?
Thank you. A very interesting presentation. I had a question regarding, I'm curious to know what was the improvement on like how much costs were reduced like after applying, or like on the data set that you had, like if you experimented on that.
Yeah, that's a good question, because right now it's very qualitative, right? It's like, oh, the traffic manager, maybe would have saved 25 minutes thinking about this problem. And now he or she is able to, complete the plan for tomorrow in an hour instead of an hour and a half, right? So we haven't gotten to that type of quantification. We are actually, so as one of the current steps is we're actually building an app that they could look on their phone and actually get some greater amount of user input for. I suppose there might be a way to translate that into dollars, but I think it's a really good question of how to quantify what is the benefit that we will see, right? Because if they are able to provide a better traffic management plan, then maybe tomorrow you save half an hour of delay, right? As an example. So yeah, the quantification question is very hard here, because it's sort of, I'm actually just helping a person with their workflow in some sense.
Right, thank you so much. Yeah.
Thank you.
Max. So I like the approach of, using AI to do the repetitive parts and the human handles the novelty. But as we're going forward into more agent-based AI and reasoning models, do you see potential for the AI to handle the unique situations?
Yeah, so I think from a strategic traffic management perspective, I think there is certainly the case that could be made for AI to provide maybe a set of solutions that, maybe the human can look at and, tailor. There's been actually a really interesting paper on using agentic AI for air traffic control. So like literal traffic separation. That came out of TU Delft a couple months ago, and it's pretty good. Like without necessarily doing too much physics-informed stuff, it's not bad at separating up to like 12 to 14 aircraft collision scenarios. That, I think, becomes a harder sell in terms of, okay, I want to replace the air traffic controller and just use this AI. What I'm in conversation with those authors and trying to think about like, okay, this is really useful. How can we, how do we make this useful? Could we potentially have like almost like little LLM guardian angels that are trained on each air traffic controller that just kind of sits in the background and maybe listens to their voice, looks at the screen, the traffic situation, and then once in a while comes in and says like, hey, by the way, you're sounding a little stressed. Also, there's more traffic demand coming from the east than you are aware of, right? So I think those kinds of almost like personalized, I don't want to say assistance, but again, sort of this guardian angel watchdog sort of framework, I think could be interesting. But I don't know if we're ready for like, we plug in the LLM right into the voice comm and have them issue commands, right, to the pilot. I think we're not quite there yet.
Is there, I mean, you mentioned that a lot of the equipment is fairly outdated.
Yes.
I actually got a chance to visit MITRE and see their innovation lab.
Yeah.
And it was crazy because it was this mixture of state-of-the-art technology and really, really old technology, like in the same workstation.
Yeah.
So I didn't get the impression that they didn't have the latest technology because they didn't have the money. It was almost more like a resistance to change. Do you think that's the root, or am I reading that wrong?
I think it's a very, very safety-oriented culture. I mean, there's a reason why these high-profile accidents got so much coverage, right? Because we're a 99.99999% safety assurance kind of industry. So I think it's just hard to get certain software certified, and it's hard to bring in new things. So I think there's a lot of people trying very hard, but the gears just turn slow for some of these, especially kind of safety critical equipment. Yeah.
Thank you.
Hello, thank you for the interesting presentation. Were there any other aspects other than GDP ground delay program considered to like expand and solve in ChatATC?
Yeah, so there's also these things called like airspace flow programs, which are, so GDPs is for an airport that you're trying to get to. An airspace flow program is for a boundary in the airspace that you are flowing across. So generally, GDPs are used when you have localized issues at an airport. AFPs are used when you have kind of en route thunderstorms or problems. AFPs are issued in basically the exact same format. So you have some nice mathematical, like nice kind of organized data, and then you have like a comment box about this AFP. So we could certainly have used AFP as well. GDPs are somewhat simpler because you can just think about this airport and the streams into the airport. AFPs, you have to think about, okay, which direction of flow does it apply to? So we just wanted to start with like a simpler problem. But AFPs are certainly something that we're looking into, as well as some other traffic management initiatives as well. Yeah.
Any other questions? Okay. Well, thank you so much, Max. That was really interesting.
Thank you.